In this video, we'll introduce a method of so-called judicious guessing. Rather than going through the integral, we, by looking at the target function phi in the differential equation on the right-hand side of the differential equation, we can kind of make a good guess about it. So here's a simple example, actually, we might have used in Calculus 2, in integral calculus. For example, computing the antiderivative of x times e to the x. And we use so-called integration by parts. It's a technique of finding antiderivative of a given function. But after we learn all this thing and we have an experience and we roughly know how the answer looks like. So what we are looking for example, in different method could be this guessing. So I'm just going to call this guessing method is the following. Maybe we're going to play with e to the x. What we're looking for is a function whose derivative is x times e to the x, but e to the x maybe is not a good, but we know by differentiating x times e to the x, we do have x times e to the x back. So let's try that one first. So I'm writing here and see what happened if we actually differentiate x times e to the x. By product rule, we have e to the x times e to the x back. This is what we want. And of course, we can differentiate this one immediately, but let's pretend that, okay, how do I get e to the x? And of course, if you differentiate e to the x, you get e to the x back. And if we have this two result, we can manipulate, keeping the so-called linearity, not multiplying or dividing each other, but simply just adding and subtracting. If you subtract these two, we get following result, x times e to the x, and minus d dx, this differential operator. And if you subtract, we get x times e to the x back. So we have this result. If we can put this left-hand side into a single derivative operator, and we're done. And because of the linearity, and you can pull this d dx out as a single operator. And again, if this is a division or product, you can't do that. But if it is sum or difference, and we know the derivative of difference two function, and some of these two functions, the derivative, sum or difference is the derivative of these two functions, a slightly different order of operation. So that becomes x to d to the x. So that's an antiderivative right there. So the answer for the problem, x times e to the x dx, we found an antiderivative, x times e to the x minus e to the x, and plus c is the constant locally. All the functions whose derivative is x times e to the x is this function plus a c. Now here's an example of differential equation, second order linear with the constant coefficients. So we can factor this operator into a first order times the first order, and you can go through integrations. That's the standard, maybe a standard method, and from there you can solve this question. But after going through in several examples, we may realize that it's actually constant coefficients. So maybe it's relatively easier to predict what happened if you apply function like e to the x and sine x and cosine x. Those are the functions, e to the x, exponential, and sine and cosine. They're not going anywhere, disappearing as you differentiate more. They're just kind of exchange each other. E to the x goes to the e to the x, and sine and cosine swap each other. They're always just there, no matter how many times you differentiate it. And you're only multiplying constants like in here. So maybe we can guess that maybe we're going to just try cosine 2x in here. So what kind of function we get out of this operator? And if you have some cosine 2x, and if you have other terms, and then you have to think about how to take care of that. So here we're going to define that operator associated with this left-hand side of the differential equation, which is second order, second derivative minus the first derivative plus identity function. So this is the operator. And what we want to solve is we wanted to solve function y such that under that operator, it hits cosine 2x. And we're not just guessing, because right-hand side is a cosine 2x. The way the operator looks like, it's constant coefficients. So if you apply cosine 2x, it's probably survive. It's there. So we're going to try L of cosine 2x and see what happens. If you differentiate this one 2 times, cosine 2x differentiated 2 times, 1 time, and the function itself. So I'll skip this part and write down the answer here. So this is the answer I got. So we're going to simplify. This is the second derivative, negative of first derivative. I forgot to change the sign. The cosine is negative, and there's a negative sign already, and y is cosine 2x itself. So this simplifies to negative 3 cosine 2x plus 2 times sine 2x. Just like when we integrate, if there's a constant multiple, we can easily take care of it. Because of the linearity, we can divide both sides and put it inside there. But here's a sine 2x, that unwanted term showed up. So you know, if you even try the sine 2x here, something like that will show up. From there, we can consider linear combination of these two results to get rid of this sine 2x. So why don't we try L of sine 2x and see what we get. I will also skip the computation here and just write down the answer. It's a negative 4, and sine 2x, differentiated 2 times. If you differentiate just 1 time, it's going to be 2 negative cosine 2x and plus sine 2x. And this, of course, simplifies to negative 3 sine 2x minus 2 times cosine 2x. All right. So if you combine linearly over just a constant, not multiplying to each other, but you can only multiply constant, and you know this linear operator behaves nicely with those linear combination over the constants. So our goal is getting rid of the sine 2x so that we obtain the cosine 2x in the right hand side. So here I underline those two unwanted terms. Since they have 2 and 3 as a common multiple, I can multiply 3 there and 2 there and see what we get. If I multiply 3 to the first equation, which is L of cosine 2x, and add 2 times L of sine 2x, then 3 is multiplied there, it's going to be positive 6. 2 is multiplied there, it's going to be negative 6. Together, positive 6 and negative 6 coefficients, they will cancel. So what we have here is a negative 9 cosine 2x, since 3 is multiplied there. Now 2 is going to be multiplied there and added. So 2 is multiplied there, so negative 4 cosine 2x. This is what happened. So the left-hand side, using the linearity of this operator L, we can combine it. Just inside, just 3 cosine 2x. This is where we use linearity of the operator L. Sine 2x here. Right-hand side is simply negative 13 cosine 2x. And what we wanted is this cosine 2x. What function hits this cosine 2x? And we will divide, because this is a constant part. This will go inside this operator again. So if you divide both sides and take that inside the operator, you can see this 3 negative divided by 13 cosine 2x. All right, let me continue here. And this is going to be cosine 2x. Another mistake here, cosine 2x. And negative 13 in the denominator is a 2 over negative 13 sine 2x there. So it had to squeeze in there. Is going to be cosine 2x. So we found the solution. Now from here, computing the general solution is adding the general solution as the homogeneous equation. So let me write that down. Well, why don't I just skip that part, the homogeneous equation we practiced. You probably practiced a lot in the earlier part. This is all about finding a particular solution, like that, and we did it. A particular solution is negative 3 divided by 13 cosine 2x minus 2 divided by 13 sine 2x. So if the right-hand side is simple as this, and this type of trying things, it just works pretty nicely. But we'll take a look at the second example, where the right-hand side is more than just one term. If we have cosine 2x and sine 2x combined it as a linear combination, then probably more standard approach will be more efficient than just trying this one and to come up with a linear combination. So the coming up with a linear combination at this stage was simple because right-hand side was simple. But if the right-hand side is more complicated, and by staring at these two equations to come up with a linear combination could be tricky, and you can of course proceed from there, but it is no longer that efficient. So the second method is going to be more efficient if the right-hand side is not just a single term like this. For example, the problems like this, we've seen that if you try sine 3x, it'll create constant times sine 3x and constant times cosine 3x. So having the same argument, 3x and 3x, is kind of coming together. So we better try most general form. We expect this thing to be the answer for this one, and simply straightforward linear algebra calculation. That will be more efficient in this case than try to figure out the linear combination of each case. So what I mean by that is that sine 3x, if you go through it here, probably it'll survive sine 3x, and cosine 3x is going to pop out. And when we try cosine 3x, and it'll have a similar combination with a different coefficient in the end. So we have to play with those two. So why don't we just try a sine 3x in there, where the L stands for, again like the last time, the operator associated with the left-hand side of the equation, and B cosine 3x. And having this constant coefficient, we expect this one looks a lot like that. So here you have to actually differentiate this one 2 times and go through this operator and that operator, and this part go through that operator. Because of the linearity, we can combine them together. So you have to do that calculation, which I will skip here and just write down the answer. Okay, when I did it, and I collected all the sine 3x and cosine 3x, and these are the coefficients. And we want this thing to be exactly 1 times sine 3x and negative 1 times sine 3x. So setting this coefficient to 1 and this coefficient to negative 1 will do it. So that will be this linear system, negative 8a plus 3b being equal to that coefficient, 1, and negative 3a minus 8b, which is this coefficient, being equal to negative 1 in here. And solving this system of equation will be the answer. You can multiply 8 and 3 here and add them together to get rid of b, and those are called elimination method. So I will skip that part, but when you do that, elimination method, you have the following answers. So it turns out a is negative 5 over 73 and b is 11 over 73. If these are correct, when you plug this back in here, they should be 1 and negative 1. So it turns out the particular solution that we're looking for is a, negative 5 over 73, goes in front of sine 3x. That was where a was. And b is a positive 11 over 73. That was the coefficient of cosine 3x in there. So with this coefficient, if you go through this operator on the left-hand side, then you will get sine 3x and negative cosine 3x back. So I think this is more efficient if you have more than two terms involved in there. But let me also think about this example, which looked like that, but is not really the same type of example as this one. I will keep the operator on the left-hand side exactly the same form like this, but on the right-hand side, I will have sine 3x, but minus cosine x like this. One difference here is that I'm keeping 3x inside the sine, but here is just the x. So trying the sine 3x or cosine 3x, you will never have this part cosine x shows up. So these are not really kind of examples that are associated with each other. So I will try separately like this, sine 3x and cosine 3x. And this will definitely gives us solution that involves 3x in the argument, and L of this two part is kind of separate problem. L of sine x, L of cosine x. These two will give you a solution that involves in sine x and cosine x. Once we figured out the combination that gives sine 3x, combination that gives cosine 3x, is you combine it because it's connected by the negative subtraction, and this will give you nicely, using the linearity L, you can get the solutions as well. So you have to actually look at this as a two problems combined together. Alright, actually I wanted to show a little bit more details, actually skipping a lot of details, so it's just showing the result actually. So think about what we did before. If we have just the sine x on the right hand side, we have to play with the sine 3x and cosine 3x without considering a times sine 3x and b plus b times cosine 3x. We can try this separately. You can easily combine it to isolate it. I find it that's fairly efficient. Suppose we did that, and we will have the following result. For example, like that, we consider the sine 3x and cosine 3x. We wanted to get rid of the cosine 3x that showed up in the right-hand side when you look at these and that separately. And using this combination, we got rid of it, although we have this negative 73 in there. Let's suppose we do the same thing separately here with the sine and cosine x and comes in together. So what is the combination in here? It turns out if you just try sine x first, these two things cancel out. It already gives you cosine x or negative cosine x. It's actually negative cosine x right here. So we have these two results. We have these two functions that goes to sine 3x, which we wanted, with a constant multiple in there. So it's not a problem. We can take care of that by putting this negative 73 inside there. We have negative 8 divided by 73. That is sine 3x there. Minus, this becomes plus 3 over 73 cosine 3x. That's this part sine 3x, but we already have a negative cosine x on the right hand side, so why don't I just add this L of sine x in there, and right hand side will be this sine 3x plus the right hand side of the second equation, which is just negative cosine x. So we got this right hand side out. So all you have to do is to combine the left hand side all together. The sine x and sine x is in there, so we're not going to combine these two, it's separate. So it's just everything inside. So as you can see, these two things interact each other linearly, and they don't. So it's just kind of separate. You can calculate it separately. This is supposed to be 3x there. So that's an example. Although it looked like complicated, you can do this separately as long as these arguments are different. Another elementary examples are this polynomial. Right hand side is a polynomial. And of course, if you're looking at the polynomial and believe maybe it was a polynomial shape and it went through this operation and became a polynomial. Because of the linearity, when this operator acting the way this acts on the polynomials, term by term, that's the part of the linearity we have it here. So if you start with a degree whatever, it'll keep that degree, and you can see it knocks down the degree and knocks down another time. And they're multiplied by the constant, so it doesn't change the degree of the polynomial. So you have to be careful when you look at the left-hand side, the coefficients of the differential equation, or the operator associated with this equation, is not constant, and you have to be careful. And usually you have a more difficult answer than what we're about to go through. But here's a constant coefficient, so you can see it must be degree 3. That's how you're going to get that. So L is going to be the same operator associated to that, the left-hand side in here. And definitely you want to try what happened. X to the third. It is not, if you stick an x to the third in here, it's not going to be just x to the third. So that's what we have to look at here, see what we get. x to the third, and you go through each of the operation, which I'll skip just to write down the answer here. Right, if you go through the differentiate and add them together, this is the polynomial we get. And what we want is we want to keep this x to the third. We don't want to touch that anymore. And how do we get rid of or change? For example, we want to get rid of this negative 3x squared that is not appearing in there. And you can see if you try x squared here, you will definitely get x squared. So let's try it here. L of x squared. If you send this x squared and through that, what's going to happen? So this is the polynomial we get out of that, and I slided this polynomial for the earlier one so that they kind of lined up with the same degree term. So here we have x squared. We definitely want to get rid of this 3x squared, negative 3x squared. Of course, I want to multiply 3 there so that these two disappeared. So let's think about multiply 3 both sides, and you will have 3 here, just 6, and 6x plus 3x squared. So as we add those together, you will have x to the third, and this one disappears. Let's do that. If I add x to the third and plus L of x 3x squared, that's the left-hand side of this and that. And this will cancel, but we have 6, and accidentally these are canceled as well, and plus 0, and so we have x to the third. So far, this is what we got. If this x to the first part survived, and we're going to think about how to get the x plus 2 part there. I forgot this is correct. But how are we going to get this x back? Of course, you're going to try L of x there. Then if you go through all this left-hand side, this is what we get. So since it has x in there, I can just simply add these two. So this time, I'm not going to write down all this thing together because of the linearity. We can bring all of them, x to the third, 3x squared, and x all inside, for which we use this linearity of the operator L. And right-hand side, we simply add the 6, so together is 5, and x came up, and x to the third. Now all you have to take care of is now this 5. So we should definitely try the constant. What happened if I stick in the constant in there? Of course, differentiate 2 times, 1 time, all of them are 0, so we get 1 right there. And here what we want is 2, so we want to subtract 3 off of that. So it's L of negative 3 is exactly negative 3, and if you add them together, now if you add this one to the left-hand side, we get inside the bracket 3x squared plus x minus 3. This negative 3 is added to the right-hand side. It's going to be 2 plus x to the third. It's kind of fun to see how this thing put together, especially it's fun to see for me, especially for me to see how this linearity kind of help us to see what is happening here. But this is not necessary. You can simply just go and, all right, I want a simpler way, more straightforward way is alternative solution. Let me write it that way. Maybe some of you will find better solution, so you don't have to juggle too much, for which was fun for me. But if you want a degree 3 polynomial here, you will definitely stick in degree 3 polynomial at max in terms of degree. So we will definitely try a times x to the third, b times x squared, c times x plus d. And see, after you went through all that, and you will have coefficient of degree 3 in terms of a, b, c, d, all the coefficient in terms of a, b, c, d, and we have to compare after you go through this operator, the coefficient of x to the third being 1 and coefficient of x squared being 0 since it's missing, and so on. From there we can compare the coefficients. So let's skip that detailed computation. I'm just going to write down the answer here. So when we did that, we have these coefficients for each of them. So let's write down the equation they want to solve. So of course a is going to be 1. That's the one equation we get. Since x squared here is missing, then negative 3a plus b is going to be 0. And third coefficient is 1, so it's 6a minus 2b plus c is going to be 1. And the last part, a constant part, has to be 2. So let me write down over here, in a different color, is a 2b minus c plus d. That part there, the constant part has to be 2. So starting with a equals 1, you can substitute back in here and get b. Once you get b and a, you can solve for c. Once you have c and b, you can solve for d. All of them will boil down to this solution in here. All right. Some of you might find this one is better and straightforward, and some of you find this is more fun to play with, and so on. But these are some of the examples I wanted to go through, called the judicious guessing. Next example, in the next part of the video, what we're going to do here is that these are the basic example. Let me write down polynomial, exponential, and what else? And sine and cosine. We went through these class of functions. Not only these are just elementary function, building blocks of elementary function, it's really easy to predict what happened with this function when you go through operator with a constant coefficient like that. If it is rational functions of rationals, quotients of this type, or more complicated, it's very difficult to predict what happened after you go through all that. But if it's simple as that, it was easy to predict what happened, so from that our guessing effectively worked. Next part is when we multiply these, some of these examples, it's still easy to predict, and we push our technique a little bit more than just these simple examples, but the product of these examples.